Last week we covered minimum spanning tree algorithms. We saw 2 examples of them. Can anyone remind me वो कौन से थे? Yes? Do you guys remember? Names of the minimum spanning tree algorithms. Kruskal and Prims. लेकिन हमने Prims को कुछ और कहा था last week. What did we call Prims last week? Yarnik. We correctly called it Yarnik because it, I think it belongs more to Yarnik to Prims. All right, so more importantly, both of these algorithms are greedy algorithm, right? Kruskal says that sort the words, sort the edges, and then add them in that order because you're looking for the total minimum weight of the edges. Or Yarnik says that at each point you grow your tree by adding the minimum weight edge that you can. And that's where we are going to start today. And today we have a new problem, which is the single source shortest path problem. We'll solve it using Dijkstra's algorithm, which you have seen so far. Before we move there, I just wanted to quickly do a short exercise. I see a lot of commotion in this area. आप लोग आगे आ जाएं, the guy with the tablet and the guy next to him. Okay, Acha. I need to talk to you today. Abhi Acha, the guy who received the tablet just a moment ago. Beto? What's your name? Okay. Do you understand what we talked about last week, minimum spanning tree algorithms? You were not there? Did you go through the slides? No? Okay. We are not having a conversation. How about you? Were you here last week?
No, sir. I went to.
Okay. Chalo, theek hai. Right. Okay. So the exercise I wanted to do with these guys was to come up with questions which are very similar to minimum spanning tree, and you think they may appear on your homework, quiz, or exam. What would you think? So try to, put yourself in my shoes. If I'm designing a question paper for you, and the topic is minimum spanning tree, what would I do? What kind of problems come to your mind? I cannot ask you to design a minimum spanning tree algorithm, right? We did that in the class. That's not going to be a question. It's going to be something which is very similar to minimum spanning tree. So what kind of problem comes to your mind? Yeah. Absolutely, that's the first thing that should come to your mind. Let's write them down, okay? So maximum spanning tree, I'm writing it right here on the board that we usually don't write on. So maximum spanning tree. And it means what you expect it to mean, that you are looking for a subgraph which is connected acyclic and total sum of the weights on the edges must be maximum over all possible things. Okay, so that's one problem. What else? What else can we do? The brute force algorithm for minimum spanning tree. We kind of covered it in class. अगर ये आपके exam में आया तो it won't be exactly like this, but still a fair question. Brute force algorithm. Does anyone remember what was the brute force algorithm for MST? Does anyone remember what was the brute force algorithm for minimum spanning tree? आप दोनों आ जाए क्या? Yes, white shirt and the girl next to you. Yes, you were definitely in my class last week. Does anyone remember what was the brute force algorithm for minimum spanning tree?
Check for all subsets of edges.
Yes.
2 to the power e.
Absolutely, excellent. So check all 2 raised to power e. All subsets of edges. By the way, this is kind of a notation that we guys use in discrete math mostly. So 2 raised to power a set means all the subsets. So 2 raised to power size of the set is a number, but this is not a number. This is a family of sets. Anyhow, all right, cool. So this is a question and its time complexity you already know. What else? Any other question that comes to your mind? Let me add something to the list. So let's say you have a graph and you constructed a minimum spanning tree on this graph. And now what I do is I add a new edge to the graph. Okay, so G is equal to V, comma E union sum edge UV. And the question is, so let's call this G prime. The question is to find minimum spanning tree of this new graph. Okay. Do you need to go through the whole exercise of running Kruskal on G prime, or is there a small, less expensive, efficient trick that you can do that will give you MST of G prime based on the MST of G? Yeah.
Cycle exists after we add this edge, then the MST is the original graph we had before. And if the cycle doesn't exist, then this
Yeah.
is the MST.
Yeah, that's the answer. That's the answer. Anyhow, so that's one. अब यहाँ पे add मैंने कहा है तो add की जगह you can also have a delete, or delete की जगह you could have a update weight. Okay, so this gives you 3 different questions based on a minimum spanning tree. What else? One more thing, couple of more things actually. So if you have an MST of your graph G, where G is this thing, is this equal to MST of the graph where I add a constant to all weights? Okay, almost implied. Similar question, is this equal to the MST where I multiply this constant to each weight? Okay, so just to give you an example, if this is your graph, or यहाँ पे you had weights 1, 2, and 3, the new graph will be 1 plus C, 2 plus C, and 3 plus C. Or second case में your graph would be 1, 2C, and 3C. Okay. Question is the MST on these 3 graphs the same MST? And if it is, so is there a condition on C? For what values of C is it the same MST? Okay. Anything else that comes to your mind? All right, let's conclude MST and move on to the single source shortest path. Again, reminder, this is a greedy algorithm, and for greedy algorithm, you are not guaranteed that it will work, right? For Kruskal and Yarnik or Prims, we had the cut property, which proved for us that those 2 algorithms work because the cut property holds. The single source shortest path problem is the problem of finding a path. You have a network and you want to go from place A to place B. Well, actually more than that is case में. The source, so let me write down the problem, okay? So the problem is you are given a graph again you have weights. think of this as a directed graph, but it's same if it's undirected. But for now, it's a good idea to think of this as a directed graphs. So let me add edges. Yeah, okay. So you have this, and you are interested, and then there is a designated source vertex, okay? So this is your input, and you are interested in finding a path from S to V for all V in your vertex set. Okay, so you're finding a path from a source vertex to every other vertex in your graph, and the sum of weights on edges F path is the critical thing, and we want to minimize it. Okay. A, B, C, D, and E. I have a graph somewhere in the slide. Let me use the same one. Where is it? Yeah, this one. Four to five. Okay, यहाँ पे edge. It's all right. Let's 4 2 5 1 4 2. Yeah, I think I messed it up. Well, it's okay. Okay, so again, I said the more practical problem is that you are starting at a vertex S, and then you want to go to some destination vertex T. The problem we are solving is that you start at a vertex S, and you want to find out the shortest path from S to everywhere. And why are we solving this problem and not the more practical S to T problem? Does anyone know why? So once again, the question is that a more practical problem is that you are at LUMSx and you want to go to, I don't know, where, airport, okay, or bus terminal, and you want to find out the shortest path from this place to a destination place. The problem we are solving here is that you are fixing the source vertex, but you are not fixing the destination vertex. You are saying that you want to find out the shortest path from S to everywhere else in the graph. Why is that? It looks like that we are doing more work than we should, Hannah? Yes, no? So the reason we solve this problem and not the original one is that we don't know a better way to solve the original problem. Okay? So to solve the S to T problem, you solve the S to everywhere problem. And both problems have the same time complexity. So we don't know how to solve the S to T problem without solving S to everywhere problem. Okay? That's where computer science stands. Anyhow, do we understand the problem? Okay, cool. So, and I assume this is already pretty motivated. तो मैं इसकी motivation में इतना नहीं चाहूँगा. But of course, the Google Maps is typical example. So what Dijkstra does, it makes the assumption first that all weights are non-negative. Okay? If the weights are negative, Dijkstra may work and it may not. We'll see that. But for now, we assume that Dijkstra works with the assumption that all weights are non-negative. और उसके बाद what it does is it at each step finds the vertex that's closest to S and processes it. Okay, so start with S. And find closest, find V and V closest to S and process it. Okay, we'll see what process means, but this is what it is. So this must be unprocessed. How do we find the closest? How do we find minimum over a set? Mini, right? That sounds like the thing that we did with the Yarnik or Prince. Cool. So a more practical way to do this would be to put S in your min heap. So let's say the priority queue is Q. You start it with S. As long as Q is not empty. Extract min from your queue. And now we have to do the processing. Okay? So this is pretty much जो हम ऊपर कह रहे थे वो करने का. All right. So what do we do next? So अभी हमने ये किया है कि we put S in our priority queue, and so we need to define the shortest distance, right? So sorry, we need to define distance, and for S, the distance is going to be 0. And in the beginning, the distance of everywhere else would be positive infinity. Okay? Cool. So to process S, what we are going to do is we are going to find out the outgoing neighbors of S and update their distances. Okay? So outgoing neighbors of S in this case, so for all U in the outgoing neighborhood of V, we are going to update their distances. Let me just make sure that I don't miss anything here. Okay, so T of D of U is going to be equal to minimum of whatever it was before. So D of U and D of V plus the weight of the edge from V to U. Okay? So weight of edge from V to U. Okay, that's how we are going to process each neighbor of S. So at this point, यहाँ पे मैं थोड़ा सा इसको अपडेट कर रहा हूँ. So I'm going to start Q with every vertex in the graph. Okay, so Q is this, और जो S का distance है that's 0, and distance of every other vertex is infinity. Okay, so just where V is not equal to S. So after I have processed S, I would have made, this was A, I guess, right? So your distance would become 2, and this distance would become 4. Okay? Yeah.
What is the plus symbol of the n mean? For all people belonging to n plus something?
Right. This is this thing, right? This is outgoing neighborhood. Outgoing neighbors. Yeah. Right. Processed means that I have removed it from my queue. And unprocessed means it's not processed. Okay. So let me just write it down here. Unprocessed means still in queue. Okay. All right. So at this point, मैंने S को process कर लिया है, तो S would be removed from my queue, जो कि यहाँ पे हो रहा है extract main के अंदर. Okay. उसके बाद what I'm gonna do is I'm gonna loop back here. Queue is not empty. Queue still has a lot of vertices except for S. And I'm gonna find the extract, the minimum in the queue now. What's the minimum in the queue now? इस ग्राफ के लिए? ये दोनों ग्राफ बहुत डिफरेंट हो चुके हैं, कुछ एजेस यहाँ पे ऊपर नीचे हैं, तो डोंट लुक हियर, यहाँ पे देखो. Okay, so S is removed from queue. S is not there. I have everything else in the queue. और C, D, and E के लिए, excuse me, the distance is infinity. For B, it's 4, and for A, it's 2. So extract min will give me A. So I get A. उसके बाद what I'm going to do is I'm going to process the outgoing neighbors of A. Okay? So outgoing neighbors of A is just C, which means that I'm going to update the distance of C to what? Bolo? No, I'm asking you the question. So what would be the distance of C now? So look here, this is what I do, right? I pick an outgoing neighbor, and I update its weight by saying that it's minimum of what it currently is, and the distance of V plus the weight of the edge. So this is my V node. Okay, so this will become now, take a guess, it's okay. वहाँ पे ना देखो, वो that graph is different from this graph. कुछ mess up हो गया यहाँ पे. Can you see this graph? Okay, so this is A. I'm processing this, and this is the outgoing edge, and this initially at this moment this is infinity. Okay, so it's going to be either infinity, or it's going to be 2 plus 1. Okay, so it's the current distance of A plus the weight of the edge from A to C. Okay, so this will become 3 now. Okay, and at this point A is processed. So A is gone. Yes? Okay, what's the minimum now? What will extract min give me? This ends? Bolo? Does everyone see that? Yes or no? Bolo koi confusion hai to. Okay, cool. So we look at C ke outgoing edges mein, this is the outgoing edge for C, and this weight will be updated to 3 plus 2, which is 5, and C would be processed. C is processed now. Block. The vertices which have been processed, उनका minimum shortest path और उनका distance fix हो चुका है. Which means कि the distance from S to A is never going to change again. the distance from S to C is never going to change again. This is 3. Okay, cool. At this point, this becomes 5. अच्छा उसके बाद I'm gonna pull B out because that's the minimum. और B के outgoing edges को मैंने update करना है. This will make this 7, and it will try to make this. Sorry. 4 plus 3 is 7, okay. So 4 plus 5, 9, but it's already 2. It will not be updated, okay. So at this point, B is processed. Uske baad I have to figure out the minimum of these two. E is the minimum. E has no outgoing edges, which means ke E bhi process ho gaya hua hai. Uske baad I'll pull out D. D ka 2 outgoing edges hai, aur dono already processed hai. But I'll try, so it will become 7 plus 1, 8. C is already 3. तो minimum इनमें से मैंने pick करना है, तो it will remain 3. And 7 plus 4, 11. This is already 5, so I have to pick minimum of 5 and 11. So 5 will stay. This completes the Dijkstra algorithm in this graph. Okay. इस example पे भी देख लेते हैं. So I'm starting with S. S को process करूँगा and I'll update the weights or distances for A and B. A will turn to 4 and B will turn to 2, I guess. Okay, so the distances is down there, okay? यहाँ पे लिखे हुए हैं. All right, at this point I'll extract min B. और B का एक ही outgoing neighbor है, which is D, which means कि D का weight update होगा to 3. उसके बाद I'm going to, so A, S and B are now processed. Okay, they assume they are not in this queue. उसके बाद the minimum is D. D has 2 outgoing edges, C and T, and they will be updated. This will become 3 plus 1, 4, I guess, and this will become 3 plus 4, which is 7. All right, so at this point the minimum is, so S, B and D are gone, S, B and D are gone, and the minimum is either A or C. So I'm gonna pull either A or C. So I'll pull and update that. उसके बाद I'm gonna pull C, and that will update my distance to T to 6. How did I get 6 in T? I get 6 by doing 2 plus 1 plus 1 plus 2. And at the last step, I'll pull T out, but T does not have any outgoing neighbors. Right. That's the complete algorithm. अच्छा, यहाँ पे मैंने I updated the distances, but I did not update it. So you know that the distance from S to C is 4, but you don't know using जो अभी मैंने किया है कि what's the shortest path that you have to follow. Okay, वो करने के लिए यहाँ पे you will need to update the parent. You will have to say, for example, that parent of U is set to V, which means that if you need to get to U, you have to go through V, and that's gonna give you a tree which has all the shortest paths. Right, so that's what we are doing here. So update the parent for each node as well. This will give us a tree for all the nodes. Okay, why this works? This is the silly picture which kind of proves the statement that it works. And so assume that this is the path that Dijkstra found for you, the path from S to D. These blue edges represent the paths. They don't represent one edge. Okay, so these are the paths. If this is not the shortest path from S to U, then there must be some other shortest path from S to U via some other edge, for example, X and Y. And assume that you already pulled X when you pulled U out and Y was not pulled. Which means कि आपको Y अभी pull करना पड़ेगा. अगर Y अभी pull नहीं हुआ तो इसका मतलब ये है कि Y का जो distance है it's more than U. Remember we were using priority min heap, and we were extracting vertices in the order of their distances, which means if I have already extracted u, the distance of u is smaller than the distance of s to y, because y has not been extracted yet. Okay? Which means that ये वाला edge add करने के बाद it will become even larger. It cannot become smaller, right? Which means that this is definitely the shortest distance. This falls apart if your edge weights are negative, right? Because if this last edge from y to u is negative, or this edge from x to y is negative, this would mean that the distance from s to y could be smaller than the distance from s to x. Okay? Cool. But in the case of all non-negative weights, this argument works, and we know that the gives you shortest path from S to every vertex in the graph, as long as the weights are non-negative. Cool. Any questions? Yeah. So let me show you a picture, I think that will explain the. Can I do it in about 60 seconds? Okay. उससे पहले इसकी time complexity कर लेते हैं. Okay. So what I'm doing is I'm adding all the vertices in my queue, and then I'm extracting them one by one. The cost of extracting a vertex from the queue is log v, and I do it how many times? How many times do I extract a vertex? Once. So this extraction ends up being log v times log v. Okay, I have to process the graph. Let me see अगर हम कुछ और करें यहाँ पे. So I relax all the edges. This thing is called relaxing, where you update the weights based on an edge. You look at the weight of an edge and see the weight of, for example, जब मैं B को pull करके ये वाला edge देख रहा था, what I looked at was कि current distance of A is 2, and if I use B, this distance could become 4 plus 5, 9. If this was smaller than 2, then I would update it. And this update is called relaxation. I'm relaxing this edge. I'm using this edge to relax the weight on A. So I'm doing this for all edges, which means that इसकी total cost E मुझे add करनी पड़ेगी. Okay? So each edge is relaxed at most, drinking at most one decrease key. Let me see. Right. Okay. So this is the cost for extract min. And for each of the edges, I'm potentially going to update the weight. Okay? And to update the weights in the priority queue takes me log n time. I use something called decrease key. So this will be E times log V. Okay? Unless you are using some heavy duty Fibonacci heap, so उस case में this will become just E times constant, I guess. Yeah. So as long as you are using binary heap, your total cost is V log V plus E log V. All right? Yeah. Okay, so since the graph is connected, E log V over is an upper bound on V log V. So ये वाला part आप लिखें या ना लिखें, it's okay. Okay. So this is equal to V plus E log V. All right? Any questions before we move on from the time complexity? Yes? So the graph is connected. If it's not connected, to you cannot find the shortest path, which means that E is more than V. If it's not connected, then the edges are. So we're assuming that it is connected. If it is connected, then the number of edges are at least the number of vertices. -1 actually, but at least V -1. Okay? Okay, let me just write it down. So अभी हमारे पास जो दो parts हैं, it's V log V and E log V. So I know that E is at least as much as this. Okay, so which means that I can write this as 2 times E log V, right? So it's an upper bound on the total cost. इसलिए हम इसको ignore कर रहे हैं. क्या? So sorry again.
What is decrease key being used for?
Decrease key is used to implement this relax part. So at each, whenever I am relaxing an edge, what I'm doing is I'm updating the distance of a vertex, potentially updating the distance of a vertex in my priority queue. So for this part, I'm using decrease key. Priority queue holds distances. Priority queue holds distances. Yeah. So at each step, you extract a vertex that is at the minimum distance from S. So it's based on the distances. Yes? Any questions on the time complexity? All right, so here's I think यहाँ पे graph है. So each of these edge represents the edge which is constructed using this instruction. Okay, so whenever you update the weight of the shortest, whenever you update the distance of each vertex, you update its parent, and that gives you a shortest path from S to that vertex using that vertex. So there's an edge from S to A. It means that this is the shortest path from S to A. I, at some point, updated the distance of A, and I set the parent of A to S. Okay? And at some point, I updated the distance of B, and I set the parent of B to S, and I set parent of D to B, and I set the parent of C to D, and parent of D to C. Okay? And this tree gives me the shortest path from S to every vertex in my graph. All right? Bolo? Make sense? All right, this does not work for the negative weight edges. And can anyone come up with an example where Dijkstra will fail with the negative weight edges? I can give you plenty of examples where it will not fail, even though there are negative weight edges. Can anyone come up with an example where it will fail? Zainab, can we add these? So these are the questions that we discussed. Can you add them in the homework 4? Okay. So this, and I think यहाँ पे कुछ है. We have 4 or 5 questions. Can anyone come up with an example where Dijkstra will fail? You have an example? Okay. Let me grab the chunk. Okay, सबसे पहले मुझे वर्डसीज बताओ. Okay, good. ठीक है. So first counter example is whenever you have a negative weight cycle, so you have a graph like this. this is S. Let's say this is 1, 2, this is 3, and this is negative 8, 4, 5, 6, 7, whatever. Okay. So इस graph में he's right. You will not be able to find the shortest path from S to T because what you could do is you could start at S and keep going in this negative cycle. This is a generic problem for all shortest path problem algorithms. That if you have a negative weight cycle, this is a negative weight cycle, right? It's a cycle that starts, for example, here or anywhere, and it gives you a path from this vertex to itself, which takes less than 0 weight or cost. Okay, so this case it's -1, I think, which means that you can loop around infinitely many times, and your cost would be negative infinity. Which means that you can go from S to any vertex, or almost any vertex, if this negative cycle is reachable in this much total weight. Which means that you can go from S to this cycle, loop around infinite times, and then go to T. Right? So this is going to be a problem for every algorithm, not just Dijkstra. Dijkstra still fails if there are no negative weight cycles. Can we see an example where Dijkstra fails, but there are still no negative weight cycles? There are negative edges, but there are no negative weight cycles. First of all, is this clear? That negative weight cycles are a problem? Right? Okay. Cool. Example where Dijkstra will fail even though there are no negative weight cycles.
Example but with plus 8 offset.
Let's see. Okay, bolo.
Same example but plus 8 for every.
यहाँ पे positive 8.
Yeah, just add 8 to every.
ऐसे कर दो.
It will become 0, other weights will become 5 plus 8, 4 plus 8, 2 plus 8, 6 plus 8.
No, I'm missing the point, I guess.
I'm saying just offset every weight with plus 8.
हर जगह पे +8 कर दो. Okay. Then okay, here.
The last one will be 0. Because the 8 plus 8 will be 0. Because it was -8.
यहाँ पे oh this becomes 0 आप ये कह रहे हो. Okay, ठीक है. So this becomes okay. This is not a problem for Dijkstra. I mean, Dijkstra would still be okay with this graph. So all edge weights are still non-negative. Dijkstra would, I don't know, Dijkstra would start here. It would go there. Uske baad it will go here. Okay, I can see Dijkstra working on this example. Because there, I mean, obviously there are no negative edges. But let's try to come up with an example. I don't have an example in my mind at the moment, but let's see. I'm going to construct the same example, but अब हमने weights को बहुत strategically decide करना है, okay? So, all right. So let's say कि मेरे पास ये वाला जो है जाना, this is -10, okay? बाकी हम देखते हैं क्या करना है. Let's say this is my direction. And let's see what matters and what does not, okay? B, C, D. Last chance to be a hero if anyone else wants to do this example for me. No? Okay. So we are trying to make an example where Dijkstra will give us the shortest path, which is actually not the shortest path. Okay? So that's the plan. Okay, I'm going to make this edge big because I want to relax this node very late in in the algorithm. Okay, so let's say this is 1, and I want to make this 1. You come here. So at the beginning, what you would do is you would use S. This will this is a running example. Okay, I don't have an example in mind. I'm constructing it as we go along. So mistakes only. So this is 8. This is 1. After I have processed S. Okay, and what do I want to do? Do I want to process this? Yeah, sure, why not? Okay, so I'm gonna process this. Okay, this is the shortest distance, है ना? D of B is 1. So I'm gonna ये वाला edge मैं अभी नहीं कर रहा इसको. We'll see इसको क्या करना है. Okay, so this will become distance from S to D is 2. Okay, let's make this 1. Edge weights are white and the distances is, I don't know, peach color. 3. Okay, so I'm going to process this, and let's say this is 1 and this is 1. So I'm going to end up with this 4. No, 3. Okay. And let me put this as 7. This edge is useless, है ना? Okay, I think we are okay here, है ना? Cool. So C is, I think, the first culprit edge node. Cool. So I'm going to start at S, okay? And the shortest path from S to C is to go from S to A and A to C, है ना? And my distance from S to C should be -2. All right. So, but what Dijkstra is going to do is it's going to start at S, relax S, update B to 1 and A to 8, distance of B to 1 and distance of A to 8. I'm not going to process 8 because 8 is bigger than 1, right? I'm going to process B. B has 2 outgoing edges, 7 and 1. This will stay 8. This will be updated to 2. Now this is the minimum weight, minimum distance node. I'm going to process D, which means that this will be processed to 3 and this will be processed to 3. At this point, this is the minimum weight node. I'm going to process this, and that's the first indication of problem, right? When you process a node, that means that वो उस वक्त shortest path पे होनी चाहिए, but it's not at the shortest path. I should have processed this node before I process this node, है ना? Cool. So this is a kind of an example where it fails. Okay, so how do we, does everyone see with this example? It's the order of the relaxation of the edges that creates a problem. Okay, Dijkstra says that process them in the current distance, which means that you could end up with processing nodes which you should not have processed before you could have processed, relaxed the edges that are leading to it. Okay, you solve it using something called Bellman-Ford. And what does Bellman-Ford do? I think it's one of the simplest algorithms there is. So it says that relax all edges. Then it says repeat v minus 1 times. Done. Okay, so and what it means is what it means. to fix here is that even if I processed some edges in an incorrect order, I'm going to process them again. Okay? So, for example, let's try to run the Bellman-Ford here with the negative weights. Let's see what it does. Okay? So, in the beginning, I'm going to I think we can do it in 2 minutes. Okay, so I'm gonna. So you start with the distance of S to be 0, and everywhere else it's infinity. Okay. And I'm gonna process all the edges, which means that I'm gonna process. I mean, in any arbitrary order. We don't care कि कौन सा edge आप पहले process कर रहे हैं. Okay, so I'm gonna. If this edge is being relaxed, so this is infinity plus infinity, which means कि infinity रहेगा. This would remain infinity. This would remain infinity. This would, I mean, infinity minus 10 is infinity. This would remain infinity. This would remain infinity. These are the only two places where it will get updated. You know? Relaxing this edge would end up making this weight equal to 1 and this weight equal to 8. Okay, so we do it second iteration. This will remain infinity, so on, so on. Sorry, on this edge, what I'm going to do is I'm going to make this negative 2 already fixed, you know, and this will become 8 again. This will become 2. I'm going to relax this edge again, but it's already fixed, right? So it's 0 plus 1 is 1. This is 0 plus 8 is 8. Okay, in the third iteration, what I'm going to do is, by the way, on this graph, how many times do I have to do this? Do I have to relax the edges? 5? Why? 4, okay, yes, 5. So number of vertices is 6, which means that I have to do it 5 times. On the third attempt, these edges will not have any effect. This edge will not have an effect. This edge will not have an effect. This edge will have an effect. It will keep the negative 2. Negative 2 plus 1 is going to give me negative 1 here. 2 plus 1 is going to give me, let's say I update this before I update this. Okay, so this will become negative 1 when I update this. Uske baad phir I'm going to update this, and this will become 3, but it's already negative 1. So I'm not going to update this. Okay, so that's third iteration. मेरा ख्याल है fourth or fifth iteration में there's nothing going to happen, and we will have our shortest paths from S to everywhere. All right, so what's the time complexity? How long does it take to relax all edges? Bolo? Yeah. Relaxing an edge is just this. If the current distance of u is less than the distance of v plus weight of v comma u, so you update it. You do distance of u is equal to this value. Distance of v plus weight of the edge from v to u. Okay, which means that this is constant, right? And I have to do it for all edges, so it's O of v, which means the total work that I'm going to have to do is order of e times v. Okay, so that's the time complexity. And can anyone just say that why I am repeating it v minus 1 time? Why this specific constant? Yes? Yeah? Right. And why? I mean, your answer is absolutely correct. Okay, if I do it one more time with time, and there is some edge which relaxes the distance somewhere, it implies a negative weight cycle, 100%. But why? Yeah.
With a negative cycle in each iteration, the edge will relax, or the distance will change.
But why specifically v or v minus 1? What's so special about v minus 1?
If there wasn't a cycle, then V minus 1 would be its MST.
You're very close to the answer. You're very close to the answer. Does v minus 1 have anything to do with paths? Number of edges? In what? In a spanning tree, that's correct. That's what she said. And that's when I said she's very close to the answer. But it's not the minimum spanning tree that v minus 1 is. Yeah. Which is a tree. So almost there, all three of you. But I want something more than that. Okay, so the thing is, we are interested in a very special tree. और tree का नाम है path, you know? The maximum number of edges in a path can be at most v minus 1. That's what v minus 1 comes from. What that means is that if you have relaxed your edges v minus 1 times, you have relaxed the edges of any possible path from S to anywhere. Because that's the maximum number of edges in a path that you can have. Okay? And if it's still being relaxed after that, it means that you're relaxing in a cycle. Okay? Cool. That concludes Bellman-Ford. And क्या आई वुड सजेस्ट कि होमवर्क 3 को कंक्लूड कर लें और होमवर्क 4 के ऊपर अब थोड़ी सी तवज्जो दे दें. Okay, it's very important and come up with interesting questions. Wednesday को we are starting dynamic programming. This is last topic before long quiz 2. Very interesting, and we are going to spend at least the time before long quiz 2 and maybe a lecture or two after that on dynamic programming as well. Okay, see you on Wednesday.